My respected teachers, first of all, thank you for organizing such a national level seminar in which we get the opportunity to participate here. I am a student of second sem from Bhattadev University. So in stage 1, my topic was that why doesn't the moon get pulled into the earth and crest? So we will see we will try to answer this question from two perspectives. One is from classical physics and one is from Einstein's new perspective of gravitational force. So what happened in 1687 when Newton gave his universal law of gravitation in Principia Mathematica? He observed that everything on the surface or near the surface of Earth, they feel an inward pulling towards the center of the Earth. Does this also true for the moon? If it is, then why doesn't the moon falling on Earth? Rather, it is orbiting the Earth. So to describe this, Newton do a small thought experiment, which were further known as Newton's cannonball thought experiments. First of all, we will see that thought experiment. So let's start our video presentation. I have a cricket ball. If I allow it to fall freely, it will hit the table in a vertically straight line. Now I will project it by giving it an initial horizontal velocity. I will project this again by increasing the initial horizontal velocity. But why the trajectory of the ball is parabolic? You can see, because at every instant Earth's gravity is acting on it during its motion. There is another factor which is opposing the motion of the ball, that is air resistance. In the absence of gravity and air resistance, the ball will follow a straight path with the same initial horizontal velocity given to it. Newton did a similar thought experiment as we seen in the previous experiment, but he imagined of firing a cannonball from the top of a very high mountain, about 10,000 kilometers high. And why he did that? Because we have seen in the previous experiment that there are two factors. One is Earth's gravity and another is air resistance, which are opposing the motion of the ball. Okay, but about 10,000 kilometers high from the surface of the Earth, the Earth's atmosphere is very negligible, so it can't oppose the ball's motion. So here gravity is only the influence on the ball. Okay. So what did Newton do? He first of all projected the cannonball with some initial velocity, and he thought that after some time traveling a distance, the ball would hit the ground at point A. If we increase the horizontal initial velocity, the ball, after traveling some distance, after some time it would hit the ground at somewhere at point B. Okay. Now you can see that as well as the horizontal displacement, the vertical displacement that the ball is traveling is also increasing. See, when we perform the experiment from the surface of the Earth, suppose this is a height, and from the top of it we perform the experiment. Suppose we projected the cannonball with some initial horizontal velocity, and after some time it would hit the ground at point A. If we increase our horizontal initial velocity, it would travel some more distance, and after some time it would hit the ground at point B. Here you can see the horizontal displacement is increasing. Okay, but the vertical distance or vertical displacement, yes, the vertical displacement remains same, because our dimension is very negligible with respect to Earth. But when you realize a bigger picture, you can see that at every throwing, when we increase our horizontal initial velocity, at every throwing, the ball cover an extra vertical distance. Okay, so you can see from A to point from B, from A point B, the ball travel an extra vertical displacement. So as we increase our horizontal initial velocity at point A, at point B, somewhere at point C, or somewhere at point D, the ball would fall on the ground. And why? Because due to the Earth's gravity, which is acting the ball towards the center of the Earth. But at some certain horizontal initial velocity, the ball would complete a revolution around the Earth. Actually, at that time, the ball is falling on Earth at every instant due to Earth's gravity. Okay, but its horizontal initial velocity and due to Earth's curvature, Earth's spherical shape, the ball is not falling on Earth. So this is the reason why doesn't the moon fall on the Earth. I have discussed this from the point of classical physics. Okay, and you can get a better idea by seeing a small animation which I made. So in this animation, you can visualize that on the increase of initial horizontal velocity, the ball is falling on Earth at different position. So this similarly, our moon is also orbiting the Earth on the same basis. Now consider the case of a rotating stone in an uniform circular path by a string. The tension in the string is providing the stone the necessary centripetal force. Now suppose this motion is anti-clockwise. Now what happens if our string breaks suddenly? We all know by Newton's first law that our stone will move at a straight path with the same velocity at which our string breaks. Now imagine what happened to moon if our Earth disappears suddenly? Does it also travel at a straight path by Newton's first law? Because we know that our Earth is providing the necessary centripetal force, which is the gravitational force. So that question troubled Einstein. Newton thought that gravitational force acts instantaneously. But Einstein thought that what happened if our sun disappears suddenly? What can we detect first? Sun's absence or Earth's escape along a straight path? Because he already discovered in his special theory of relativity that nothing can move faster than light. It takes light 8 minutes 20 seconds to travel from sun to Earth. So how can gravitational force act instantaneously? So Einstein modified Newton's gravitational force. He included gravity in his special theory of relativity. He told us that to understand the whole universe, we have to unite space-time together. He gave us the concept of space-time continuum, the fabric of space-time. Now, this fabric of space-time is smooth, continuous. Now, I am showing here you. This is actually, if I told you in a simpler thing, then the fabric of space-time is like a net. Actually, this is not feasible, but we imagine such a conceptual model to describe the motions of planetary objects and the all universal things. So I am representing it here in 2D, but actually what happens that in 3D it looks very complex. So I am representing it in 2D. Now, anything, any matter, any energy present in the space-time fabric, it creates a dent in space-time. So what if any matter or any mass present here, then it looks like this. I am drawing it again in below. So there is some suppose that this is our mass, then the space-time looks like this. So the mass creates a dent, it creates a curve in the space-time. As much you get closer to the object, to the mass, the space-time fabric gets more curvature, it becomes more dent. You can visualize these things very easily by the diagram I am showing you. Now here you can see the presence of our Earth causes a small dent in space-time. When something, suppose our moon, moves close to our Earth, it feels this dent in space-time and rolls around Earth like a marble rolling in a bowl. So this is true for all the planetary motions. So finally we have discussed the question that why doesn't the moon fall on Earth from two perspectives. One is from Newtonian physics and another is from Einstein's new perspective, which is general theory of relativity. On the basis of Newtonian physics, today we are able to send a satellite in space, and on the basis of Einstein's general theory of relativity, today GPS system works. So what once started with Newton, it leads us to Einstein's general theory of relativity. So this is the actually the historical event which we discuss through the question that why does the moon fall on Earth. So thank you very much.